Okay, we have spent a week or so talking about one-dimensional motion, and the natural extension to that is now let's think about, in general, 2D or 3D motion. And so the first thing that we need to do is reevaluate our quantities that we've been working with, so things like position, displacement, velocity. So first off, position, in one dimension we basically just had position as x, or position is y, or position is z. Well, in our 2 or 3 dimensions, basically the position vector, you just add up those individual x positions, y positions, z positions. And so if you write that in unit vector notation, you get this. So the x function in the x direction, the y function in the y direction, and the z function in the z direction. So that's position. Displacement, same definition, just the difference in the position at two different times. We're just using r now for the general position. And then velocity, same definition. The velocity vector is the time derivative of the position vector. And when we take the time derivative of the position vector, now that we've got three different functions, the x component of the velocity is just going to be the time derivative of the x position. The y component of the velocity is going to be the time derivative of the y position. And then the z component will be the time derivative of the z position. So our 2 or 3D velocity vector then is just in component form: vx in the x direction, vy in the y direction, and vz in the z direction. So one of the most important things to appreciate and understand, and we're going to watch a few demos on this, we're going to look at a few sample problems. The big conceptual thing with, let's start with 2D motion, is that the motion along the perpendicular axes are independent. And so what that means in practice is that the x motion is independent of the y motion, which is independent of the z motion. And so this figure that I've grabbed from the book highlights this. So we've got two objects that are going to be released at the exact same time. The red one is going to be dropped, and the blue one is going to be thrown horizontally, so in the positive x direction, which I've defined here. So released at the same time, red ball is dropped, blue ball is thrown to the right. Now, if you watch what happens in the diagram, initially the two objects are at the same y position, and they're offset a little bit in x just so that you can see them. And then sometime later, they've both dropped the same amount. The blue object, though, has traveled a little bit to the right because there's some x velocity. In the next snapshot, they both have, again, dropped the exact same amount, and the blue object has moved even further to the right. And then, again, still falling at the exact same rate. And so if you look at the y position, the objects have the exact same y position the entire time. Now, why is that? Well, the objects had the exact same initial y velocity. The objects had the exact same y acceleration. If this is throwing two balls, this would be free fall. So the acceleration would be down at a rate of 9.8 meter per second squared. So the y motion here is exactly identical for the red and the blue ball. What's different is the horizontal motion. So the initial horizontal velocity for the red object is 0 meters per second. And the x acceleration in free fall, the horizontal acceleration, is 0 meter per second squared. So that means the x velocity for the red object is 0 meter per second the entire time it's falling. What about the blue object? Well, the blue has some initial x velocity. Let's say plus 1 meter per second. So plus because it's to the right. Well, since there's no x acceleration in free fall, right? No horizontal acceleration. That means any time during the fall, that blue ball is going to be moving at plus 1 meter per second to the in the horizontal direction, so 1 meter per second to the right. And so what we end up getting is that the only difference in the motion here is essentially how far away from the red ball the blue ball lands. Right? The x motion is the only difference. The y motion is exactly the same. And so what we're going to be doing in two-dimensional motion problems, which will be the primary multi-dimensional problem that we work on, it's 2D. What we'll be doing is breaking our 2D problems up into two 1D problems, a y motion problem and an x motion problem. And when we do that, then we revert back to our three kinematic equations that we've been using in one-dimensional motion. We just now have to solve two problems that are linked together essentially by time. And of course, our last motion quantity from 1D motion is acceleration. And the same idea here, the acceleration, it's got the same definition. Now that our velocity is defined to have an x, a y, and a z component, our acceleration vector, right, has each of those components. And just to point out that acceleration, which is the time derivative of the velocity vector, but velocity is the time derivative of the position vector, so our acceleration vector is actually the second derivative with respect to each of those x, y, and z positions. Alright, so that two-dimensional motion that we were just looking at with the red and the blue ball, the objects in free fall, that's typically referred to as projectile motion, which is one of the most common types of 2D motion that we'll look at. Another common type of two-dimensional motion is circular motion. And so we're going to go over a little bit here how to think about circular motion. So the main concept that I want you to think about here is that in one-dimensional motion, when an object accelerates, there's basically two options. It's either speeding up or slowing down. But that is not the only two ways that an object can accelerate. An object accelerates when the velocity changes, and velocity can change in magnitude, but it can also change in direction. Now, in 1D motion, essentially changing the velocity direction isn't really an option because there's no turning, because we are restricted to move along one axis. But in two-dimensional motion, now all of a sudden we have the opportunity to have not only the magnitude of the velocity change, but also the direction. And so what we want to focus on first is something known as uniform circular motion. So this would be objects that are traveling in a circle at constant speed. So anytime I've got this circle here, anytime in the motion the object is moving at the same speed, so these vectors are the same length, but the velocity vectors are pointing in different directions, and so that necessarily means that there's a change in the velocity, so this object is accelerating even though it's traveling at constant speed. And so, again, this is called uniform circular motion when we're traveling around the circle at constant speed. And the acceleration has a specific name because this is acceleration that's associated with changing direction as opposed to changing the magnitude of the velocity vector. And this is known as centripetal acceleration. And the centripetal acceleration vector, if you look over here in this picture, centripetal acceleration points towards the center of the circle. So I've got my object here traveling around this circle. My velocity vector points off this way. The acceleration vector points perpendicular to that velocity vector towards the center of the circle. Now the magnitude of the acceleration is v squared over r. So it depends on the speed at which you're traveling around the circle, and it depends on the radius of the circle. And again, the direction here is towards the center. This is centripetal acceleration.